All right, so here we are finally moving into some of the more exciting parts of calculus. So we'll just jump right in here to 2.1. So hopefully by now you've watched the 7-minute Khan Academy video where he is introducing the concept of a derivative. If you haven't done that, I want you to stop and just go watch it. It's 7 minutes and it's just a good, very simple introduction to what a derivative is, and it just helps when you can hear different explanations of a concept from different people in different ways. That's why I want you guys to watch that in addition to these notes. This right here, this page 96, why calculus, and these other pages, obviously is in reference to pages of a textbook that you guys do not have, so you can disregard it. But I'm going to jump right down here to tangent line to a curve and why we use calculus. So there are actually two different main categories of calculus. There's differential calculus and integral calculus, and we are focusing on differential calculus in our time with Calc, and that has to do with, as hopefully you gathered from the Khan Academy video, slope at an instantaneous point on a curve. So we've talked so much about slopes of lines, and we've never really talked about slope of a curve because it's always changing. So integral calculus, just as a quick little intro, deals with area underneath a curve, which is kind of an interesting thing. It's another very simple visual for us, but we've never really talked about, if I've got this, what would the area be under this curve, because its boundary is constantly changing. So it's still very similar, and it's relating to that constantly changing rate of change, but talking about area underneath the curve. So we will not be dealing with that integral calculus. Instead, you guys will hit that next year if you continue moving forward, but we will be focusing on differential calculus. So we're going to jump right here to this curve and looking at the tangent line to a curve. So from that video, or maybe just from your previous knowledge, you guys probably remember that when you've got a line that crosses a curve at 2 points, we're looking at a secant line. And when we have a line that crosses a curve at 1 point, we're looking at a tangent line. And so when we are talking about the slope at this point here, where it's marked tangent line, if I want to know the slope, the instantaneous rate of change of the curve at that exact point, it's actually the slope of the tangent line at that point. So that's why, and that slope is the derivative. And we'll get to that here in another few minutes. So what is your definition of a tangent line? That's just a line that touches a curve at exactly one single point. So a tangent line touches a curve at one single point. Okay, I actually forgot to mention this in the beginning of this video, but it is hard to do this if you don't have a printer at home, but you guys will be fine. So for those of you who have a printer at home and you're able to print out these notes, please do that. It's going to help you a lot just having some of these visuals worked out. If you don't have a printer, no problem. Obviously, these visuals are going to be hard to replicate perfectly, but moving forward, when we're just looking at problems, you guys, I would encourage you to just pause and rewrite the problem on your own paper. You need to work through these problems to get that practice. So if you don't have a printer, it's no problem. It's not a huge disadvantage. Just write it down on your own paper. Obviously, I can't be there to make sure you're doing that, but it's going to be really hard to learn this content if you're not writing anything down. So follow along on your own notebook paper, stay organized, and take the notes just like you would in class. You might just need to pause to write some of the problems down. Okay, so now we're going to get to, go back up here. What is this? How would I determine the slope of that tangent line? We don't have a formula for slope at a single point. What we do know is how to find the slope between 2 points. So this secant line that I drew, I could easily, let me mark this, with ordered pairs. Let's say this first point was -1, -1, right here. And let's say I graphed a second point of 5, 4. Well, I have 2 points, and I could easily get the slope of those 2 points, between those 2 points, and calculate that change in y over change in x. So we're going to apply that, but that's all we really need to know to build a formula for the tangent line, because what we want is this single point, and we want the instantaneous rate of change right there, not 2 points. But we're going to start building that by considering the situation where we do have 2 points. So I'm going to start by breaking down what's in this, what seems to be very complicated image right here. Again, if you don't have the notes packet, just follow along and listen and write down what I write down, but you don't need to replicate this image. I'd rather you just focus on understanding it. So what we have here first is, you'll see me tracing along the curve of the function that we're interested in. So we've got this purplish curve right here. Then we have 2 points on that curve where our secant line intersects it. So what our goal right here is to find the slope of a secant line. So right here sorry, I didn't even introduce this. To find the slope of a tangent line on this curve, we start by finding the slope of a secant line. So we can do that because we have a formula for finding the slope of a line if we know 2 points on that line. So I know this point, this is at x1, and we've got x1, y1, and then I know this point here is at x2, y2. We all know how to get the slope of this line. We know that the slope of that secant line is the change in y divided by the change in x, rise over run. Whoops. So let's look at our y values, and we will subtract them. So our y values are just denoted by y2 and y1. So if I want to know this rise, all I'm doing is subtracting the y values, y2 minus y1. And when I want to figure out the run, the horizontal distance, I'm doing x2 minus x1 to figure out that. Okay. All right, so now we're going to so this right here should not be confusing. It should be very straightforward and review. But now let's see what else we have here. We've got this delta x and this delta y. So remember, delta is a Greek letter that in math we use to represent change. So from here, from this x1 to this x2, there is a change in x. So it's just using delta x to represent the difference between x1 and x2. So just to clarify, I'll write down here. So from this x coordinate, this is our x coordinate that we're going to have. This is going to be our main kind of focus for x. The change from here to here is x plus whatever change in x we have. X plus some change in x to get us to x2. So now I'm going to talk about these two coordinates in terms of x and f of x. So just to clarify, if this is x, then its y value is f of x. That's just our fancy way of saying y in function notation. So I'm just going to put f of x right here. And then this point right here, which we were calling x2, I'm actually just going to call that x plus delta x now because I want to refer to everything in terms of x and delta x. So this x2, we arrive at it by taking our x value and adding some change in x. So that's what gets us to here, which means this point up here is now f of x plus delta x. So let me notate that. So this point right here is the x value, x plus whatever change in x we added to it. And that means this y value is f of x plus delta x. So to order that, to label that, that's going to be an x value of x plus delta x, comma, and the y value, think about what that would be, it's just going to be f of that x value, f of f plus delta x. This ordered pair down here we saw was just x, comma, f of x. So I just want to clarify, instead of saying x1, y1, like we did right here, I'm calling it x, comma, f of x. And instead of calling this x2, we're actually calling it x plus delta x, which is just whatever number I'm adding to x to get to here. So the y value of that is f of x plus delta x. So this may seem overwhelming and complicated. I'm just rewriting my x and y values in terms of function notation. X and f of x, and then our second one is x plus delta x, and then f of that number as well. So now that we have these new ways of writing our ordered pairs, now let's fill that in for the slope of the secant line. So the slope of the secant line, we're taking our two y values and subtracting. So y2, which was written here this way, which was over here, instead of y2, I'm actually using this new way of writing it, f of x plus delta x. So our slope is y2, which is f of x plus delta x, minus y1, which is f of x, divided by x2. So here's my x2, which now we're calling x plus delta x, minus x1, so following my formula, minus x1, which is just x. So this is our new formula for the slope of that secant line. And what we can do now is simplify that just a little bit, because you'll notice in the denominator we have x and negative x. So the final formula for slope of that secant line, so the slope of that secant, I'm just going to put secant right here, is f of x plus delta x minus f of x. So I've just done y2 minus y1 divided by x2 minus x1, which actually simplified to just delta x. Okay, this is the slope of a secant line of any curve that crosses any curve at 2 points. That's an important concept to understand. So if after watching this, the last few minutes of this through one time, you're looking at this and saying, what the heck just happened? That is a normal reaction. There's a lot of notation on here. There's a lot of writing and letters and symbols. So I would encourage you to go watch this again. Just rewind a few minutes, watch it again, understanding where this in red comes from. The slope of this secant line is fundamental in understanding the definition of a derivative. It's just, I think the challenge is just getting past all of the technical notation to get down to what it really means. So I would encourage you to rewind a few seconds if you need to. Okay, so we've only started with slope of a secant line, and our goal is to use that slope, the formula for that slope of a secant line, to build the formula for the slope of a tangent line. And remember that tangent line is only touching the curve once. So what I want you to imagine, and it's hard to do this just on a piece of paper, but all of these several lines here, so follow my red dot here. This is initially where the second point is, where this original secant line crosses this function f. So all of these other ones are what's happening when you see my red point go down, and it's getting closer and closer and closer to x naught, that little x sub 0. That's our original x value. So see, what we have here is this change in x, and we have that change in x. We want that change in x to get smaller and smaller and smaller. So imagine these 2 points getting closer and closer and closer together. So really we want that change in x, that delta x, to approach 0. And as those 2 points get closer together, as that change in x approaches 0, what we have is this secant line actually approaching what will be the tangent line, where it touches only at one point. So now we need to rely on this concept of something approaching 0. And thankfully, we do have a way of representing that with limits. So limits, remember, are as some x value approaches another value. So taking the limit as delta x, this change in x, we want that to get smaller and smaller and smaller. So we've got a single point on our curve, and then we have the result of the limit of that will be the slope of that tangent line, because as the 2 points move together and form just the single point, we've got the tangent line. So this is the definition of a derivative. So that's the result of taking the limit as delta x approaches 0 of the slope of the secant line. So that's why we started with slope of a secant line, because if I take this whole expression and take the limit as delta x approaches 0, then I've got the slope of the tangent line. So that's the limit of f of x plus delta x, that's my y2, minus y1, which was just f of x, divided by x2 minus x1, which we saw simplified to just delta x. So this is the formal definition of a derivative. Now, instead of just starting with this complex formula, I wanted to slowly build it, because again, it's the value of understanding the concept of what a derivative is so much more valuable than learning all of the shortcuts and roundabout ways to calculate the derivative. When we get into the next section where you guys learn those shortcuts, it's going to be easy for a lot of you, but understanding this concept is really important. So in terms of understanding calculus. So again, what I'm circling right here in the purple is the formula for a derivative. What is a derivative? It is the slope of a tangent line at a single point. Slope of tangent to a curve. And why is that important? The slope of a tangent line to a curve tells us instantaneous rate of change at any given point on a constantly changing function. So that's something we've never been able to really talk about yet, which is what's so cool about calculus, is now we're talking about rates of change for an ever-changing function. So now we're going to take this formula and apply it and practice using it with a few functions to find the derivative, to find the slope of the tangent line. All right, so let's actually apply this and start understanding a little bit. So turning the page, we have the derivative of a function rewritten for us, along with some notation that you guys will see. So we see the definition for the derivative of a function. So the derivative of a function f at x. So when we talk about the derivative of a function, we can find the derivative, aka slope of the tangent line at that point, for any value of x. So we can choose any x value we want to find the derivative. We can also just find a formula to find the derivative at any value of x. So here we have the formula written out again. It's just the same exact thing we built on the last page, but we see something interesting out front, and that's this f with this little apostrophe x. So we write, this is what the typical notation for derivative you're going to see, and we would call that f prime of x. So this right here is f prime. That's what we would say in words, but we denote derivative typically with just that little tick mark. So other notation that you'll see in the Khan Academy video mentioned this as well. And the reason there's so many different notations for this is just because there were so many different mathematicians who, once calculus sort of started blossoming in the mathematics world, you had a lot of different guys studying this stuff. You typically will see f prime of x. You will see y prime as well. That means the same thing. You'll see dy over dx. Again, it's still representing slope, change in y over change in x. We just see the d typically for that derivative there. We also see d over df with f of x next to it. And then we see capital D x with y in the brackets. All of these represent derivative. And remember, I care that you know what derivative means. So derivative, just to reiterate, I'm going to sound like a broken record. I realize that. I'm going to write it out again. Derivative is slope of a tangent line. Slope of tangent to a curve. And think about what that means. So we've got derivative equals the slope of a tangent line on a curve. And what is the slope of a tangent line? That's the instantaneous rate of change. Instantaneous rate of change. And instantaneous because it's constantly changing. The rate of change is constantly changing. So we can only talk about rate of change at a single point. It's that moment's rate of change, that one single point's rate of change. So let's talk about, so we've seen the visual of that, and now I want you guys to apply it to some problems mathematically. So I do realize if you do have a printer and you're working through this, your problems are actually laid out a little different. You've got number 1 here and then number 2 over here, and I put number 2 down here. I will try and make it so it's easy for you guys to follow along with this, but my advice for you going through these problems is write small because there's a lot of notation in writing for these. Okay, so example, find the derivative of f of x. So with this, when we're asked to find the derivative, what we're really asked to find is the slope of a tangent line at anywhere on this function. So we're going to jump back to the formula. We want to find the derivative of this, and now we have a formula for the derivative. We know that the derivative of f is going to be f prime of x. That's what we call it. We know that we're going to find that derivative by taking the limit of the slope of the secant line, which again, I'm pulling this directly from up here. The limit as delta x approaches 0 of f of x plus delta x. So here's the thing. We know what f of x is. This is f of x. I'm underlining it. I'm circling it right now. So f of x plus delta x, all I'm doing is changing my x to x plus delta x. Like if I told you guys, don't write this down, I'm just going to jot it down. If I told you here's f of x, calculate f of 5, what would you do? You would plug 5 in, you'd multiply 2 times 5, then subtract 1. So when I tell you to calculate up here f of x plus delta x, think about what that means. We're doing f of x plus delta x. That means literally plug this expression, x plus delta x, into our function where x is. So again, you do not have to write this down because we're going to write it down again in a second. But this would be 2, and instead of x, where earlier I plugged in the 5, now I'm plugging in this expression, x plus delta x minus 1. So this is how we would represent f of x plus delta x. We're just plugging in x plus delta x to our function. So I'm going to get rid of all that and then apply what we just talked about to our actual formula here. So my eraser on this app does not work, and that's why I have to get rid of everything one at a time. Okay, back on track. So going back to my formula, we are taking the limit as delta x approaches 0 of f of x plus delta x. So I'm taking x plus delta x and directly inserting into my function. So that would be 2 x plus delta x minus 1. So that is this piece of the formula that I'm circling. Then I'm subtracting f of x, meaning I'm subtracting my function 2x minus 1. So I'm going to do minus f of x, which is 2x minus 1. So this is my numerator, and I'm going to actually highlight pieces, hold on, let me finish this, all over delta x. Okay, so if you're concerned about where some of these came from, I'll use this highlighter here to help show you. So I've got, okay, f of x plus delta x is this. So that's where I took the expression x plus delta x and plugged it in to my function. So instead of 2x minus 1, I have x 2 times x plus delta x minus 1. Then the other part of the numerator came from, let me choose a highlighter here, minus f of x. So that would be minus 2x minus 1. So that's where those two pieces came from. And then obviously we have the denominator coming from what I just highlighted there. So that's how we've just built the application of the formula to this problem. Now we're going to simplify. Okay, so moving forward to simplify this. All right, so the derivative f prime of x is the limit as delta x approaches 0 of, so I'm actually just going to distribute my 2 to both of those. So that would be 2x plus 2 delta x. Then I have this minus 1. And then, so that was this minus 1. Now I'm distributing my negative to the inside of that parentheses, so that would be minus 2x plus 1, all over delta x. So if you're wondering why I didn't just immediately do direct substitution, remember that's our first strategy, is take whatever delta x is approaching and just immediately substitute that in, and what we would end up getting is 0 over 0. So that's why I should have addressed that first, but that's where I just started by simplifying this as much as I could to address the fact that I can't use direct substitution yet. So now if we continue simplifying, hopefully you'll see in the numerator what happens is I've got 2x here and negative 2x there. That's convenient. I also have negative 1 here and positive 1 here. So let's begin by canceling. Those are gone. And then negative 1 plus 1 is gone. The only thing remaining in my numerator is 2 delta x. So as I continue simplifying this, I've got the limit of, as delta x approaches 0, of 2 delta x over delta x. Delta x over delta x is just 1, so this is actually the limit as delta x approaches 0 of 2, which is always 2. So what we've just done, applying this function, or applying this formula for the slope of a tangent line, aka derivative, we have come to the answer of 2, meaning the slope at any point on this function, regardless of what x is 2. Now, half of you may have started this problem with me thinking to yourselves, I already know that the slope of this function is 2 no matter what because it's a line, and I can just see that the slope is 2. So some of you may have just kind of not even thought about that because we're just in this zone of derivatives. But yeah, of course, this function always has a slope of 2. It's constant. So we knew that in the beginning. Now we just proved it by using the derivative. So we're going to apply it to one more problem only for this part 1 of this. So this is like a bulky section just because of this big new concept. So I'm just going to do one more problem and stop there, and then we'll pick up where we left off in a different video just to give you some time to process this. All right, so moving forward to example 2. Again, write small because there's just a lot of expanding and simplifying for these problems. So in number 2, we want to find the derivative of this function, f of x. So the notation, to find the derivative, what I'm really looking for is f prime of x. We know from our formula above, so take a look back above, glance up, and you'll see what I'm going to do to find the derivative is take the limit as delta x approaches 0 of my numerator, which is going to be f of x plus delta x. So again, all I'm doing is plugging in the entire expression x plus delta x in for each of these two x's right here. So that would be 3, and instead of x squared, it's x plus delta x squared minus 2 times x plus delta x plus 1. So right now all I've written, let me highlight again because I think that kind of makes it easier to organize. I have this entire thing. Maybe that does not help simplify things. So that first, this is f of x plus delta x. The next part of the formula is to subtract f of x itself. So now I'm going to subtract f of x, which is just the entire function 3x squared minus 2x plus 1. So that is the minus f of x. So this whole, top expression, this is my numerator. Just to reiterate, because I know this is overwhelming, this first bunch is f of x plus delta x, and the second piece is f of x. So the numerator is always f of x plus delta x minus f of x itself. The denominator is always over delta x. Okay. So evaluating this limit from our strategies from chapter 1, we learned that ideally we could just directly substitute this value 0 in. If we did, what we would actually end up with, imagine if we plugged 0 in here, basically we would have f of x minus f of x, and we would have 0 over 0. So there's always typically going to be some manipulating we need to do to simplify and then get to a point where we can use direct substitution. Okay, so first we need to, in the numerator, I need to square x plus delta x and then multiply it by 3. So that is kind of like a big old chunk of work that I'm going to do off to the side over here. So you can think of it any way you want. If you prefer, where's my pen? Okay, so if you do x plus delta x squared, you're really doing x plus delta x times x plus delta x. So you would distribute. If you are more comfortable with using an area model, do that. And I'll do an area model sometimes, and sometimes I'll just do the distribution. So let's think about what we would have here. We would have x squared. Then we would have delta x times x, and you can just write that as delta x times x. And then in the top right, we would have x times delta x, which is still just delta x times x, so 2 of those, plus delta x squared, so delta x times delta x. Okay, so when I go rewrite my limit, this is why I said write small, because there's so much. Do not skip steps in this process, because the whole point, again, when you're using the limit process to find a derivative, you're basically proving what the derivative is and how you got it. All right, so this piece right here I just did. So I'm just going to leave that 3 out front and then simplify. I've got x squared plus 2x times delta x, or delta x times x, so delta x times x plus delta x squared. Oh boy, that's just the first thing. Then I have this next piece where I'm going to distribute negative 2. So that's negative 2x, so minus 2x minus 2 delta x. And I'm going to have to get rid of my area model so I have some space. Okay, then I have this plus 1. Then I need to distribute this negative to all of these three terms. So that would be minus 3x squared plus 2x minus 1. So that is the beginning of my numerator being simplified. I'm going to continue moving forward, and notice that I'm taking the 2 seconds it takes to write, maybe 5 seconds, the limit as delta x approaches 0 each time. Okay, so now I'm just going to distribute this 3 to my 3 terms in that parentheses, and then I can start canceling things out, and you'll notice every time you'll notice these convenient cancellations. So I've got 3x squared plus 6 delta x times x plus 3 delta x squared. Then as I continue, let's see, actually, but when I continue, here we can already do a couple of cancellations because I have this minus 2x here and plus 2x here. So actually in that step, I can go ahead and I'm going to do that now. I also have this plus 1 and minus 1, so I'm actually going to cancel those out too. So the only two things I have left to write for my numerator are minus 2 delta x and minus 3x squared. So that sign in front of it comes with it. So negative 2 delta x and negative 3x squared. Okay, and that's all over delta x still. All right, before we see if we can do this direct substitution, I still have more ways that I can simplify my numerator now that I've distributed everything I can. So hopefully you see this 3x squared and this negative 3x squared. So we can do that. Those are gone. Another good thing we can do is if you notice in our numerator after canceling out the 3x squareds, notice now that every single term, I forgot I can change my little pointer guy. So every single term, 6 delta x times x, 3 delta x squared minus 2 delta x. Every single one of these terms has delta x in it. There, there, and there. So what I'm going to do is actually factor out that delta x from the terms in the numerator only. When I do, I'll be left with 6 times x, because I've factored out the delta x from that, so that just leaves me 6 and the x, plus 3, and when I factor 1 delta x out, I've got 1 remaining. And then when I factor delta x out of this minus 2 delta x, I just end up with minus 2 all over delta x. So we finally get to this point where we have two factors up here, delta x and this chunk of stuff, divided by delta x. Finally, I can make that cancellation and say, okay, delta x over delta x is simply 1. Now what I've got is a limit as delta x approaches 0 of 6x plus 3 delta x minus 2. And now I'm in a position where I can use direct substitution because there's no errors or problems in substituting 0 in for delta x right here. So if I substitute 0 in for delta x right there, then my limit through direct substitution ends up being 6x minus 2. So we have this final derivative, f prime of x equals 6x minus 2. So it's a very long process to get there, this limit process, but what we've just done is found that the slope of the tangent line, so think about our original function, 3x squared minus 2x plus 1. Hopefully you guys know now that this is a parabola. I don't know exactly where this parabola is. I'm just going to put it on the graph. So we know that this parabola, its rate of change is constantly changing. So if we're talking about rate of change right here, it's the slope of the tangent line right there. If I want rate of change right here, it's the slope of the tangent line right there. If I want rate of change here, it's the slope of the tangent line right there. So what this has done, this final formula for derivative, this has given us the formula to calculate the slope at any single point on that parabola. All I have to do is plug x in here. So when you see f prime of x, again, I want you to drill into your brain, that is the slope of the tangent line at x. So let's say I wanted to know what the slope of the tangent line was when x equals 1. I would just plug 1 in here, and it would get 6 times 1 minus 2. That's 4. So it would have a slope of 4. Obviously, I graphed this parabola terribly, because if the slope is 4 at 1, this function must be increasing at 1. So maybe if we just graph a standard parabola, at 1 the slope would be 4, meaning it had a slope of 4 right there. Okay, so this is a lot. I understand these are hard, bulky problems. It's a big new concept. I want to stop there for now to get you some simple practice with definition of a derivative. And then we'll move forward with more complex problems next time. All right, you guys, talk soon.